Hi Chemistry. Today I'm going to introduce Le Chatelier's principle, go over the basics, and keep it fairly simple. In the following classes we're going to dig into it more. It's not too bad, and it's something I really enjoy in this unit. Okay, so Le Chatelier's principle describes how a chemical system at equilibrium responds to a change. These can be changes to the concentration of something in the system. That's what we'll talk about today. Later we'll talk about how to deal with changes in pressure and changes in temperature. Alright, so to frame this, I want us to consider this equilibrium system, hydrogen with iodine producing hydrogen iodide. Made a typo in the word consider, made an O, turned it into an I. Pretty smart, right? So, I've got initial concentrations there, and what I want us to do is sketch a graph indicating how the concentration of each of these entities changes as equilibrium is achieved. Okay? In order to do that, we need to find all the equilibrium concentrations. We only have hydrogen iodide, but this is all we need to complete an ice table. So let me flip the page. So I'm ready to go with my ice table. I got the initial stuff there. Check this out. We can complete the change to the hydrogen iodide and then multiply by the molar ratio. It's going to be 1/2 for each of these guys. So I'm just going to do this quick because I think everybody's doing a great job with ice tables. It's going really well. Okay, so those are the equilibrium concentrations of each entity in this system. Okay, now let's see how that's going to look like in a graph. I've just got some axes here. I'm going to expand upon this graph in a later video, so I'm just going to take it to this point. I'm calling this time. So this is the reaction coordinate as the equilibrium is set up, as the system starts. I'm not going to use a ruler. I'm going to eyeball most of this stuff, but I'll try to do a good job with it. All right, so I've got a couple of different colors. I'm going to use blue for the reactants, and then I'll use red for hydrogen iodide. So hydrogen starts at a concentration of 2 moles per liter. I'm going to put that here. Okay, so this is going to be H2. Right, double that will give me I2. Okay, so this is the concentration on this axis. Okay, I'll label everything in the reaction coordinate down here, which is like a time, a stand-in for time. All right, so let's just talk here. Hydrogen goes from a concentration of 2 moles per liter to 0.5. Okay, so I'm just going to highlight where 0.5 might be. It might be right here. Okay, and then iodine goes to 2.5, which might be, I don't know. It's going to be above where hydrogen started. Ooh, by about that much. Okay, this looks fine. Okay, so those dots indicate the initial concentration. So iodine is going from 4 to 2.5. Hydrogen is going from 2 to 0.5. I can maybe label these now. 1, 2, 3. This is a 4. Okay, moles per liter, should have mentioned. My graph's coming together. Okay, let's talk about the shape. Iodine starts up here, ends here. You're not going to connect this with a straight line because that would tell you that the rate of reaction is constant. So where do you think the rate of reaction is going to be greatest? At the beginning or at the end? Well, the way equilibrium works is equilibrium occurs when there's no noticeable reaction. So the reaction has to be slowing down as it gets to equilibrium. I'm saying at time t is equilibrium. Okay? Another way of thinking about it is at the beginning, there's only hydrogen and iodine. So they're going to react really quickly, but as they form hydrogen iodide, the reaction is going to slow down because there's fewer of these guys to bump into each other. Okay, so I just want you to agree, think about it, and I want to convince you that the graph should look like this. So steeper at the beginning when the reaction is happening at a greater rate, and they should be totally flat at equilibrium. And these two graphs should look about the same, just starting at different places. Okay, for you calculus people, this is concave up. Okay, now let's talk about hydrogen iodide. It starts at 0, ends at 3, which would be about here. Okay. Again, the reaction is greatest at the beginning. It's got to flatten at the end. But when you're increasing, that's going to look like this. Okay, so this is our hydrogen iodide, how its concentration is changing. Okay, for you calculus folks, this will be concave down, negative concavity. You guys know all about that. All right, now let's talk about what's going to happen when we shift something, when we add something to this container.